ఆమె కూడా స్టార్ట్ చేయాలి. దానికి పంపిస్తే ఒకసారి చూడండి, ఓపెన్ చేసి మళ్ళీ చెప్పండి. చేయండి, ఏం పర్వాలేదు. నేను అదే రిసోర్స్ పర్సన్ చేంజ్ అవ్వాలో అర్థం కావట్లేదు నాకు. నేను దీనికి
సిగ్నల్ లేక వాట్సాప్
ಅವರು ಇಲ್ಲಿ ಒಂದು ವಾರ ಸರ್ ನಾವು ಹೇಳೋಣ ಸರ್.
వస్తుంది కదా లైవ్. వస్తుంది కదా. ఇంకా స్టార్ట్ చేయలే, అందుకే ఇది పెడుతున్నా. ఇప్పుడు చూడండి ఏమొస్తుందో.
Good morning, everyone. I invite everyone to first day of the 5-day FDP on recent technologies in computer science organized by Department of Engineering Technologies of G. Pullareddy Engineering College, Autonomous, Kurnool, Andhra Pradesh. I now invite Dr. R. Pravinsam sir, Head of ECS Department, for the opening remarks and declare the start of the FDP. Please, sir.
This conference will now be recorded.
Shabana madam.
Sir.
Yes, madam. Can you continue?
Yes, sir. Yes, sir. Hello, sir. Can you hear me? Hello, everyone. Can you hear me?
Yes, ma'am.
We can hear you.
Okay. Thank you. So, good morning to everyone. I invite everyone to first day of the 5-day FDP on recent technologies in computer and science, organized by Department of Engineering Technologies of G. Pullareddy Engineering College, Autonomous, Kurnool, Andhra Pradesh. I now invite Dr. R. Pravin Sam, sir, Head of ECS Department, for the opening remarks and declare the start of the FDP. Sir, please, sir. Pravin Sam,
Okay,
sir.
madam. Thank you very much.
Okay, sir.
Is it audible, madam?
Yes, sir.
Yes. Good morning, all of you. I welcome you all to this 5-day faculty development program on recent trends in computer science, organized by Department of Emerging Technologies in Computer Science. On this occasion, I would thank our Honorable Principal Sir, Dr. B. Srinivas Reddy Sir, for his continuous support in organizing this FDP. And also, I would like to thank the management for providing the necessary resources without which this FDP would not have been possible. At the outset, I would like to congratulate Yes Shabana and her team in bringing out this 5-day online FDP from 20th to 24th of this month. Technology today is evolving at a rapid pace, enabling faster change and progress, causing an acceleration of the rate of change. However, it is not only technology trends and emerging technologies that are evolving. A lot more has changed this year, making IT professionals realize that their role will not stay the same in the contactless world tomorrow. The main technological factors which are bringing the change are IoT, robotics, big data, and 5G. These technological factors would revolutionize the way we live and work in the future. In spite of busy schedule, all of you are present here to gain the knowledge. I feel at the end of the 5-day online FDP, all the participants would be gaining the knowledge of recent trends in computer science that would be discussed in the FDP. Thank you, one and all.
Thank you very much, sir. May I now invite Dr. K. Govardhan Reddy, sir, Dean of ECS Department, to say a few words about the department. Please, sir. Govardhan Reddy, sir.
Madam, is the voice audible?
No, sir. Your voice is audible, sir.
Okay, madam.
Okay, sir.
Yeah. Good morning, all. Myself, Dr. K. Govardhan Reddy, Professor and Dean, Department of ECS. Welcome you all to the 5-day online FDP on recent trends in computer science. So I feel it honored to give brief overview of our department. So the Department of Emerging Technologies in Computer Science is established in the year 2002. The department offers various courses under its umbrella. Department has the Computer Science and Business Systems (CSB) with an intake of 60. Computer Science and Engineering in Data Science (CSD) with an intake of 120. And Computer Science and Engineering in Artificial Intelligence and Machine Learning (CSM) with an intake of 120. The department offers honors program in CSB, CSM, and CSD. The curriculum of the students is exposed to emerging topics such as data analytics, artificial intelligence, machine learning, cloud computing, and Internet of Things, etc. to make the students industry ready by the end of the 4 years of their course. To provide training and introducing new innovative courses based on the industry demands, the department is trying to collaborate with national and international institutes, R&D organizations, and software industries. The department is headed by Dr. R. Praveen Sham, a visionary who is marching towards the development of the students, faculty, and staff. So finally, I appreciate convener of the FDP, Srimati S. Shabana Begum, and co-convener Mr. V. Suresh, and all the faculty coordinators for organizing this 5-day online FDP. Thank you. Thank you very much.
Thank you, sir. Let me give the overview of the FDP. This is S. Shabana, convener of this 5-day online FDP on recent trends in computer science. When I spoke about the FDP to my head of the department about the topic on which the FDP has to be conducted, he said that topics on the emerging technologies would be of great interest. So I started looking for the resource persons. When I spoke of the Dr. Lokanathan Veeramuthu sir, Research Assistant Professor Taipei, University of Technology, Taiwan, he was ready to stress on significance of flexible composite material in IoT and robotics. I thought that this would be of great interest. Today, world is of the interest and in that data in playing an important role. So the second day would be of challenges in big data by Dr. Vishal R. Dahiya. Madam is professor at Indus University, Ahmedabad, Gujarat. As the world is progressing towards the 5G communication, we too would be interested in it. The third day would be on 5G communications by Suraya Mubin. She is associate professor at CMR Technical Campus, Hyderabad. On fourth day, Mr. Srinivas Ellappu is the principal architect at Vizio, Dallas, USA, would be enlightening us on IoT. Everyone knows that Java is the universal language and Spring Boot is like the wings of Java. So to focus on Spring Boot, Mr. Girikumar Panam from IOS IT Malaysia would be dealing with it. The number of participants registered are 1079. The GoToMeeting supports 250 participants at a time. If more number of participants are there, YouTube link will be provided. Participants can join through the YouTube for FTP and will share via WhatsApp. I request everyone to maintain dignity and not post unrelated things in the chat box. And also do not use foul language in the chat box. I request everyone to maintain dignity of the FDP. If you are having any queries or questions, you will be allotted the time at the end of the sessions. Participants can raise their hands and the respective participants will be unmuted. Once the session is completed, during the feedback link will be shared. Once all the 5 days of the FDP are completed, certificate will be issued to all the eligible candidates. Now I request Mr. V. Suresh sir, Assistant Professor and co-convener of this FDP, to introduce today's resource person, Dr. Lokanathan Veeramuthu sir. Mr. V. Suresh sir, please.
Thank you, madam. Good morning, everyone. I deem it a privilege to introduce today's resource person, Mr. Loganathan Veeramuthu. So, sir is working as Research Assistant Professor in Institute of Organic and Polymer Materials Research and Development Center of Smart Textile Technology, National Taipei University of Technology, Taipei, Taiwan. So, sir has a previous work experience of postdoctoral researcher in Organic and Polymer Materials Research and Development Center of Smart Textile Technology, National Taipei University of Technology. So, coming to sir educational details, sir has completed his BSc in Chemistry from Ramakrishna Mission, Vivekananda College, University of Madras from 2010 to 2013. MSc in Chemistry from Ramakrishna Mission, Vivekananda College, University of Madras from 2013 to 15. Sir has worked as Project Assistant, Central Leather Research Institute, Council of Scientific and Industrial Research from 2015 to 2017. Sir has acquired his PhD doctoral from Organic and Polymeric Materials Research and Development Center of Smart Textile Technology, National Taipei University of Technology. Sir research interests include electrospun, nanofiber technology, wearable electronics, smart textiles, perovskite, and optoelectronic devices. To his credit, he secured second rank and first class in the BSc degree examination in the Department of Chemistry, Ramakrishna Mission, Vivekananda College. Also, secured First rank and first class in the MSc degree examination in the Department of Chemistry, Ramakrishna Mission, Vivekananda College. Sir participated in national level internship program at Indira Gandhi Center for Atomic Research, Kalapakkam, Tamil Nadu. Also received Best Student Award from Ramakrishna Mission, Vivekananda College in the year 2015. Sir also presented various papers and posters in national level and international events. To his credit, he has 17 research publications in various journals and articles and 1 book chapter. Also, Sir served as a resource person for the international webinar on next generation technology towards smart textiles organized by Chalapati Institute of Engineering and Technology. Served as a resource person for the international webinar on upcoming trends in wearable electronics and Internet of Things conducted by National Institute of Technical Teachers Training and Research. Mr. Loganathan also served as a resource person for one of the 1-week national level online faculty development program entitled Recent Trends in Artificial Intelligence and Cyber Security organized by Sri Vishnu Engineering College for Women. So with this brief introduction, now I request Dr. Loganathan sir to
What does it
take
mean?
over.
Active voice. What does it
Sir?
mean? It means that if 0 is coming, that means output is coming. If 1 is coming, that means output is not coming. Because the IC
Okay, thank you, Suresh sir. I will feel that with your vast experience, you would enlighten our participants, sir. May now request today's resource person, Dr. Loganathan Veeramuntu, sir, to take over the session. Sir, you will be made as the presenter. You can share the slides and proceed with the session, sir.
Sir, we can't hear you. Sir, we can't hear you, sir. Loganathan, sir. Hello, sir. Sir, you are not audible, sir. Sir, we can see your video, but audio is, we can't hear you.
Participants, we request you wait for few seconds. We inform the same issue to the sir. He is just checking to, towards his end. Thank you.
Okay, sir.
Yes. Now?
Sir, it's audible, sir. Thank you.
Yes, yes, yes. Okay, now I'll try to share my screen. Can you give me the access?
Yes, sir.
Yes, okay. Thank you. Okay, yes, I got the access. Now let me present my screen. I'll go for my presentation here. And yeah, okay. You hide everyone. Yes.
Sir, please make it as presentation. Sir.
Yeah, yeah, yeah.
Yeah, thank you.
Okay. Now, yes, okay. I
Yes,
hope
sir.
everyone can listen to me now. Everything is fine. Yeah, let's start the presentation. Sorry for the delay because of the technical issues. Okay, yeah. So today topic is functional polymeric composites for multifunctional applications. And yeah, in this first topic, we are going to see about not directly related to computer science, but yeah, because my research field is like multidisciplinary, and we know that in recent years, not only one field is going to work in your real-time applications. You need everyone to co-work. For example, you need chemist, physicist, material science background. Everything has to be put into one field to get a final product. So yeah, it's crucial time to work with our issues, and we have to address them with our wholesome knowledge, not with only one field of knowledge. So it's necessary to understand the principles and what kind of materials is suitable for our applications. Those kind of things are quite important for the application part. So here I'm going to introduce something like functional polymeric composites, and yeah, let's go into those topics in the upcoming slides. I try to move my slides now. Yeah, okay. First of all, I'd like to introduce where I'm staying in and where I work. And here, this is the Taiwan map you can see, and in the northmost part, you can see Taipei. And here, this is 101 famous building, which is having 101 floors and which is the tallest building in Taiwan. And here we can see this is my university, Taipei Tech, shortly known as, and this is in Chinese, National Taipei University of Technology. This is the main entrance. And yeah, now, yeah, first I'll start with the question. Why we need innovations in material science and computer science? Why we need those? Okay, let's go. Okay, the current scenario is we know that many of them are first or aware of something like smart cities, smart homes, and smart mobiles, smart watches, everything becoming smart. And why it is becoming smart? Because we know that we are going to impregnate or integrate some components into it. For example, your phone, in the beginning, it was only, you can make a calls, and now you are able to connect them visually, and you can also feel them by using some AR and VR techniques, right? So it becomes more smarter and smarter. And yeah, there are many other applications. In the beginning, we just use the textiles just for the protection of our skin in order to prevent the health of our body system. So now it is transforming into the next generation textiles, like it is becoming smart. Even like not even only your phone and TVs are getting smarter now. Your textiles are also getting smarter. And in the recent years, you might have seen many different kind of textiles which is having different functionalities, not only for preventing your skin. It is going to monitor your health or something like that. So yeah, let me get into those things. Okay, yeah, apart from that, sensing or monitoring, it's crucial time, because we know that we have some energy crisis. In order to get some non-renewable energy sources, we are using some natural fossil fuels like that. We are going to process them and extract the energy out from them, right? So it is not that good for the environment, and which is creating a lot of carbon emissions, which is having impacts in the global warming. So in order to avoid those things, we should rely on something like renewable energies, or you should have some energy storage system, because we know that we can extract the solar energy, wind energy, all these things, where we are going to store this kind of energies. So it is quite important to make them in order to get some energy sources, or if you want to store them in the different form, then how you can do it. So there are many ways to do it, so we can look into those things. And now I would like to stress the importance of something like inorganic conductive fillers. And we know that fillers is nothing but anything we are going to blend with our system, which can be considered as fillers. For example, I'm saying conductive fillers. We know that in the usual case, what wires we have some conductive material like copper or silver or aluminum, right? So in this case, I'm saying about conductive inorganic fillers. It's like bulk material, which is like, So in order to get some better functionality, if you want to impregnate into your wearable system, you should rely on something like nanomaterials, nanotechnologies, in which, we are going to use some nanomaterial based materials, something like nanotubes or nanowires, quantum dots, or something like carbon sources like graphene or quantum dots or diamond quantum dots, like that. There are many ways, and these kind of conductive fillers are going to be helpful in fabricating some sensory devices. So that kind of sensory devices can accommodate your bodily strains, or if you have stress in your body, it's going to create some impact on your devices. So your devices may malfunction. So in order to avoid that, you should rely on something like novel materials. So how we can achieve those things? By tuning your material property. You can fine tune by using some nanotechnology applications. Like there are different fabrication methodology we can adapt, or else you can also use some structural engineering. Like here you can see there are different structural patterns we can form by using the nanotechnological aspects, right? So, and there we can apply this kind of sensors. We can use it for different application in order to see the voice modulation or detection, or if you want to see the blood pressure, glucose level, all these things can be done using this kind of conductive materials. So now I'd like to introduce something like energy aspects. Here we can see there are two different categories. One is you can use this kind of materials for sensory applications that can be used in our IoT systems, Internet of Things. Everyone is in recent years, everyone is aware of Internet of Things. Why we want Internet of Things? Because we know that whatever data we are going to get from our sensors, if you're going to impregnate your sensory devices into your body or just patch them on to your body, okay, so on that type of cases, you are going to extract the outputs, sensory outputs. If you want to transport that outputs to your phone or to your medical practitioner, you want to contact your doctors, and your doctor wants some data. So how he can get those data? By your this kind of IoT system. It can interconnect your data with your outputs to your targets, right? So this is how it can be done. And everyone know that in the past, we know that they are using some glucose sensors, handy portable devices. Now I'm going to speak something different, not like that kind of rigid devices. I'm going to say about flexible devices or stretchable devices or self-healable devices, those things. So now we can see there are different kind of energy resources we are going to utilize. And we know that solar, thermal, and mechanical energy, or that kind of mechanical energy harvesting, we need to use this kind of generators like piezoelectric generators or triboelectric or electromagnetic generators or hybrid generators. Not because we know we are very well aware of something like solar cells. That one is getting older, but still it is going to give a huge impact in our renewable energy systems. And thermoelectric is nothing but you are going to harvest your body heat, or the heat source energy can be harvested. Because we know that thermo means nothing but your temperature, right? So that kind of thermal energy can be transduced into your electrical energy. That energy can be helpful for your sensing or energy harvesting part. So now here, this is another picture in which we can highlight the importance of wearable devices, sensory devices. In this, you can see for pressure monitoring, you can see like this, or tactile vibrations you can sense. Or if you have some temperature monitors, you can sense whether you are feverish or you have some hypothermia in your system, then you can easily monitor. there are many methods to monitor those things, and there are many mechanisms involved in it. So if possible, I can expose you to some of the very few important mechanisms available. And here you can see how they are connecting the wireless communication system. I already showed you, I already exposed you to by verbally. Now you can see how it is pictorially represented. You can see there are many different kind of sensors for ECG or EMG, smart band to monitor your temperature, or EEG, this kind of sensors. There are different sensors going to be put onto your body, and you're going to extract the outputs. Then you can connect with the wireless communication system. For example, okay, sorry, I can use highlighter or spotlight. Okay, yeah, here you can see the wireless communication system. Through that, we can contact our medical practitioners, and we can diagnose by our smartphones. This is how it works. So, okay. Sorry, I'm not able to move the screen. Okay. Now I'm fine. Yeah, so Internet of Things is going to be the major field, and which is going to connect, interrelate every field, not only technology for transport, agriculture, smart cities, security system, energy harvesting. If you want to track them, it is important to utilize this kind of IoT based system. So you can interrelate all these kind of fields into one portal. So it is quite important to use these IoT systems. And apart from this kind of sensory applications, this kind of self-powered tissue repair system can also be done, because here you can see this kind of flexible energy harvesters or energy generators. You are going to put them onto the wounded area. For example, if you got some damage on your skin, in this you can see how the sensors are placed and how they can monitor this wound healing performances, because we know that the cell viability is quite important for the wearable devices. If we are going to fabricate some wearable flexible devices that can be put onto our system, then it is going to give some electricals. If you're going to pass some current or voltage to your system, then that is going to create some electrical stimulation. That kind of electrical stimulation can promote the wound healing. So it's quite important to use this kind of haptic device, which can easily cure your illness in that way. And here we can also see the elderly care applications. For example, your grandparents are alone, or they are abandoned, they are in very far city, they don't have proper healthcare system. If you want to help them, in that cases, we can notice the performance, or if you want to see their health status, then you can easily use this kind of IoT based system. Using cloud systems, you can extract the data. And apart from this kind of IoT system, there is something like direct techniques. Here we can see they are showing two different systems here. Use spotlight, wearable electronics and wearable photonics. Why we need wearable photonics? Because here we are going to transform the electrical outputs via transmitter and receiver system. Then you're going to use them, and you can diagnose, or you can see all the big data collections, and you can analyze the patterns, health patterns, something like that. But if you want to see them in the real time itself, you don't want to interconnect your device with other devices, you can directly see with your wearable device itself. For that, you should prepare something like wearable photonics. In that, you can see visually, you can see the results easily. So it's quite good to impregnate these two fields together, wearable electronics and wearable photonics together. So here we can see there are different kind of nerve muscle stimulation system, in which they are showing some mouse models. They use some mice to control their stimulation patterns, and then they can see their nerve stimulation, how it happens, or muscle regeneration, how it can be happen using this kind of self-powered systems. So it is quite interesting for medical fields also. And okay. Oh, sorry. Okay. Basics of materials and its significance in technology. Now I have shown you the importance of IoT systems and healthcare and wearable electronics, where it is going to be helpful, right? So how we can form that kind of devices? what is the major component for that kind of devices? Anything you start with electronics, you will start with something like electrodes. You need some conductive material to start with. For that, how you can prepare this kind of conductive materials, and especially how you can make them as not like a rigid material. You want something like flexible or stretchable materials. So how you can prepare? You need to rely on something like materials called polymers. So we know that in our high school itself, everyone have studied something like polymers. It's a big chain of molecules where there will be many monomers getting, like a blocks. Then you will be ending up a big molecule called polymers, right? So in this case, I'll try to discuss few polymers which is commercially available. That kind of commercially available polymers can be used for flexible and stretchable wearable electronics. So now I'll try to introduce some of the methods they use to form this kind of conductive polymer electrodes. There is something like in situ electrochemical polymerization. In this, they use some electrodes and then they pass the current. Then they'll try to deposit some conductive materials over your flexible polymeric substrates like that. And this one, what I want to discuss, because this is my field, electrospinning. In that, I'll discuss very detailed in the upcoming slides. I don't want to introduce now. And the other methods, there are many different methods to form polymeric conductive electrodes. So what kind of conductive materials are available? Here you can see this graph is showing the conductivity details about different materials ranging from insulators, semiconductors, and conductors. So it depends on your conductivity level or range. Depending on that, we used to classify them as insulator or semiconductors or conductors. In our case, we are focusing on conducting part. So there are different polymers like polyaniline, polypropylene, P.PSS, or polyacetylene. There are many different polymeric conductive materials, but the problem is their conductivity is not it's not comparable to our traditional metals. So how you can improve the polymeric conductive fillers conductivity? So that we have to rely on something like blending or forming some hybrids or composites like that. So we'll try to fine tune our morphological characters. For example, we'll try to shift them from 0D, 1D, or 2D, 3D materials. Like that, we try to tune them. And now I'd like to introduce a material called perovskites, and this is the structure. You just consider this as your some of the mineral, and which have the structure like this. Like here, you can see there are many cubes arranged in this way. Okay, and here we in the corners or face or in the middle, you can see there are many atoms. So now these kind of materials are going to give some impacts on our wearable devices. How come it is going to give some such impacts? So let's go into those topics. And now this is another pictorial representation. Here we can see the perovskite structure and where they are going to be used, because everyone know that solar cells are getting very famous in the past few decades, and in the recent decade it is getting very familiarized because of perovskite based solar cells, because in the past they used some silicon based solar cells, and silicon is getting rare. But in this kind of perovskite based solar cells, we can form very cheap solar cells, but the problem is their stability is not that good. So how they can improve the stability of the perovskite materials? And this is how the structures look like. They can form 0D structures, 3D structures, or 2D structures based on perovskites like this. And we can apply them in different fields, not only in solar cells, LEDs, thermoelectrics, or piezoelectrics, or artificial synapse like that. So here, this is another material called yamexing. Here we can see they are like sheets. You can consider this like you just try to represent it. Represents like a book. There will be many sheets, right? So here you can see this is our precursor. In that case, MAX on the right top corner. You can see this is the basic component we start with. And then we try to etch this aluminum part. If we can etch this interlayer, then we'll end up with something like 2D structures. These kind of 2D structures are very important. in terms of sensing, catalysis, or biomedical application, energy storage, harvestings. Yeah, so there are many different characteristics for this kind of structural materials. Their structure and their stability is going to have a greater impact in their application part as well. And this one is to highlight the significance of some natural based carbon quantum dots or graphene quantum dots. Here we can see, because we know that carbon everywhere, anything you burn, you'll end up with the carbon, right? So the same strategy they use, but they use different techniques to process them to end up with the small, minute particles called quantum dots. And quantum dots are very important in terms of optical and electronic properties. So here we can see there are different methods they use. For example, they start with the hydrothermal or solothermal, and something like laser techniques or microplasma or some sonication methods or microwave methods to form this kind of carbon quantum dots. So methods and the fabrication methods and the material property and how you make them cost effective, that is quite important. And here we can see here I'm going to highlight the significance of our renewable energy resources. You can see this graph is implying the energy consumption in industry or in transport, buildings, and in heat collection, those kind of things. There are many carbon emissions is happening every day. So how we can reduce the carbon emission by using this kind of renewable energy sources. So this is quite important. And in terms of wearable devices, these are all the factors we should be very concerned about. Like we need some power source, and it should be lightweight, and it should be smaller in size, and it should be washable, and the fabrication should be facile, and it should be connectable with other devices, and durability. So these kind of things are quite important. And in this case, you can see the electricity and heat. It's very important in terms of different application like transport, industry, and residential purpose services. So in this case, you can see the trend in the market growth. You can see the wearable electronics market trend is getting higher and higher, and it is anticipated that it will grow several billions in the upcoming years. So this field is a hot topic. Everyone can consider to do some research. If you are interested in, you can work on this kind of field, which will be having very good appreciation. You will be getting very good appreciation in the upcoming years. And now I want to stress the different ways of doing smart textiles, because you can see this is like conventional system. They use some bobbin and spindle, and they form some conductive yarns like this kind of structure. This is a microscopic view. Here you can see the core and shell structures, and this is cross-sectional image, and this is from top view image. You can see the difference. And they use some commercial elastic yarn composites, like in our spandex or something what we use in our conventional system. That kind of elastic systems can be used for sensory applications. And in this case, they are using some spacer fabric, like that in the shoes we use some Velcro, like that kind of systems, right? One will be very rough and the other side will be smooth. It will be like a spacer fabric. That kind of fabric systems can be used for pressure sensing. So that kind of systems can also be done facilely using this kind of textile based devices. And this is another method in which they are forming the wet spun structures, in which they can form 1D structures like fibers, like our wire. You can form 1D structures using this technique called wet spinning. And in this case, you can visualize how this kind of strain sensors work. I said the importance of conductive materials and how they tune the conductivity, or how they form very good conductive materials by using some hybrid structures. So in this case, you can see, I said about hybrid structures. Here you can see this like a sphere, and these are like plates. So this is a hybrid structure. In the initial stage, it will be like this. It has some interconnection, so the conductivity will be very good. But if you're going to strain them to a particular extent, the electron percolation, you can see the electrons will be passing like this from your plates to your particles. Through your particles, it can conduct the electricity. But if you are going to strain to a certain level, until that threshold, it can be acting as your conductive material. But if you cross that threshold, you won't be able to get the electrical percolation. So that time it will change its conductivity. That means your resistance will go higher. So with that kind of strain monitoring, that can be used for the sensory application. And in this case, I'm saying about hybrid structures. And in this, you can see they are using some elastomeric material, and then they coat some conductive material. The black one is your conductive material, you assume, and then you're going to strain them. You can see the crack propagation happens. The crack gradually grows. So that means your conductive particles are losing their electron flow. So if you're going to strain, if you're going to put this kind of fabrics in your fabrics, and if you're going to work out, then you can see the extent of your workout by monitoring your resistance or conductivity. So this is for 1D structure. The same way they can be done in thin film structures. They also optimize their microstructures or buccal structure. That kind of things can be done. And this is a recent article, and in this you can see they are showing the extent to which our body can exert the strain. For example, here you can see elbow, shoulder motions can give up to 37%, or hand motions are going to give 43% strain to your device. So from this, we are getting to know that at least 30 to 50% body strain your device can accommodate. It should accommodate, or else your device will easily fail if you are going to fabricate some wearable devices. And in this case, I'm going to highlight the market growth in terms of smartwatches or wristbands or clothing. You can see the smart clothing there. Percentage of growth is getting very high in the recent years. And then here, the wearable electronics, how the number of publications or patents are getting higher in the recent years, and how it is going to be helpful in forming this kind of electrospun structures plus wearable electronics. It's gaining more and more attention in the recent years. So wearable electronics have quite good demand in the real-time application. And in the recent years, we also published some wearable light emitters, like light emitting diodes, LEDs, right? So this is a schematic in which we can see how the stretchable LEDs can perform under flexion or stretching. Those kind of things can be done using some perovskite based LEDs. And this is another article in which we are using some perovskite emitters, and then we use some self-healable polymer. Even under, if you're going to cut your device, it can heal like our skin. It is going to mimic like electronic skin. That is what we sometimes we denote them as e-skin, electronic skin. So this kind of wearable electronics are quite important, because we know that when we are going to use some electronics for 1 or 2 years, it may have some damage. If you're going to drop your phone, it's going to damage. So you will be losing your money, or you are going to create a lot of waste that's going to affect the environment. So in order to avoid those things, you can fabricate this kind of self-healable wearable electronics. So it won't, even after damage, it can heal by itself and it can stay robust. So it won't create any e-waste. So it's quite good for the environment, and you can also save your money. So it's quite good. So in the recent upcoming years, you can see a lot of self-healable electronics. That is going to be the trend. And here we can see they are showing different kind of structural patterns. This is not like you cannot see with your eyes. You can use some microscope or SEM or TEM to see this kind of structures. Why they want to fabricate this kind of buccal structures or microbells, serpentine structures or nanomesh kirigami patterns? Why? Because I already said that our body is going to exert a lot of stress and strain to our system, wearable system. So our system should accommodate that kind of stress and strain, or it should dissipate that kind of stress and strain. How we can dissipate them? By using this kind of structural aspect. It's quite important to control this kind of micro or nanostructural architectures in your device. Then we can successfully form this kind of different sensors. For example, you can put them on your glasses, for smartwatch or smart mask. You can do many things with this kind of structures. And then here you can see how this wearable sensors is going to be connected with the internet and how you can transfer, and it can be connected to your physician and you will be getting your feedback with your phone itself. You don't want to transfer, you don't want to spend money on your
Hello, Lokanatham sir. Call you.
Now I think everyone can hear me. Ma'am,
Yes, sir. Yes,
am
sir.
I
Yes,
audible?
sir. Yes, sir.
Okay. So from which slide I have lost my voice, from maybe 20 here or here?
Yes.
I was speaking here before.
No,
Yeah.
sir.
So yeah.
Yeah, 23rd, sir.
Okay. Yeah. So yes. Okay. Yeah. I'll continue with this. So this kind of structures, I'm highlighting the importance of this kind of structures. Why we want this kind of micro or nano structured materials? Because I already explained that if you're going to use the materials onto your body, it's going to experience a lot of stress and strain. So your wearable device should accommodate or dissipate that kind of energy. So how you can dissipate effectively by using this kind of structures? So we can modulate the structures by using our nanotechnology. So this is how they can modify. So if we can modify the structures of our sensors, then we can finally get very good internet connection. Then using some 5G communication, you can easily transform all your data to your healthcare systems. Then your physician can analyze your data. Then he can give the feedback very easily to you. He can get back to you very fast. So it won't take long time for you to help. You can usually use this kind of nanostructures or nano-based sensors for the healthcare system. And now I want to highlight the importance of 1D structure, nanofiber structures or microfiber structures, how we can prepare this kind of micro or nanofiber structures by using this kind of different techniques. Now we'll start up with the melt blowing. Melt blowing is nothing but we put our polymers and then we heat them, and we try to push them with through the spinneret. Then you can collect them. You just pass some cool air to make them solidify. Then you will be ending up with our fibers, and you try to adjust your winder speed and the heating rate, all these kind of things. Then you will be ending up with the different morphologies. This is how they prepare 1D structures. Or if you want to prepare some centrifugal or force spinning, which is nothing but it resembles like our cotton candy maker. In the cotton candy maker, we put some sugar solutions or sugar, and then we just heat or we rotate them. Then we'll be ending up with our cotton candy, right? The same way here, they are going to put our polymers and then heat them and rotate them in the high acceleration. Then you will be ending up with our fiber system like that. The other way is blow spinning. Blow spinning, they use some compressor. They use the air to blow them. So with that pressure, they will be forming very small, minute fibers. Then that kind of fibers can be utilized for the fabrication purpose. So there are different methods to form. So now I like to introduce my technique, and this one here you can see natural fibers. But natural fibers have fibers. I'm not meaning that natural fibers cannot be used in the intelligent system. I mean that we can easily control synthetic polymers, and with the help of nanotechnology, we can fine-tune our morphology very easily up to nano level. So it's quite good to use a very simpler way to process, right? So it is quite good to implement this kind of fiber system. And here we can see the coating method. In the beginning, when we want to form some super hydrophobic textiles, how we form? We just take our conventional cotton textile, and then we put some hydrophobic material, and then it will be getting coated like this. Here you can see the functional materials on the top of our fiber. Then you will be having your something like biofouling if you want to avoid anti-biofouling, or if you want to create some hydrophobic substrates. It can be done using conventional way like this. But if you want to use something highly more stable systems, then we can prefer this kind of wet spinning or electrospinning systems. It's quite easy to do, and then it will be having very good stability as well. So we prefer using this kind of systems like wet spinning or electrospinning. And this one looks like very simple. You can see it's like a bi-scrolling. They are just forming this kind of structures, and then they scroll them, and they'll end up with this kind of structures. You can see like this. It's like a spiral form. And so the current wearables are like 1.0. They have smart glass, smart bands, and smart watches. And what will be the next generation wearables will be like this, invisible. You cannot see your devices. Actually, it will be very small, and it will be transparent, soft wearable devices. And like a tattoo, it can be looking like a tattoo, so no one can visualize how the devices would be the next generation. So nanofibers. Now I want to introduce the electrospinning setup. This is the basic setup. Here we can see we use the pump, and then we use a syringe. The pump is going to push your polymeric solution, and then we pass some voltage here. Then you can collect your fibers. This is the basic setup. And with that, if you can tune your solvents and other ratio, then you can control your fiber morphology from smooth, porous, or hollow structures. Because if you want to create some hollow structures, what we can do, we'll use some hollow structures. Means you want to create a space, then you can create some water soluble polymers, and then you can solubilize your polymer. Then you will be getting this kind of hollow core sheet structures. So there are many different ways to prepare. And this is another method called coaxial spinning. Here we will be having two different solutions. One is core solution, the other one is sheet solution. So if you spray them, you'll be getting like a wire-like structure. Inside you'll be having core, and the outer part you'll be having your shell polymer. So this is quite important. You can adjust your fiber morphology and you can tune your morphology very easily using this kind of electrospinner setup. So there are different ways to prepare, and there are conjugate spinning. You can see they are using this kind of melt spinning and blowing method, bubble spinning, vibration spinning, magneto spinning. They use some magnetic field to control. So there are many ways, and they also use different kind of collectors like tube way or funnel type collectors, and they use some bath collectors. They use some solvent based system to collect and then ground the electrodes like that. So there are many different ways to prepare the fibers. They make some small fine tunings to get their optimized fibers very easily. So you can also try if you are interested. And this is the recent article we published, and it is open access. If anyone is interested, you can look into the details of how they prepare fibers and what kind of factors are going to affect your fibers. Flow rate or distance between the needle and the collector, voltage, solvent, viscosity, polymer concentration, and where this kind of polymers can be used. What is the importance of conjugated copolymers, all these things. This is more based on material aspects. And this is another article we published in Chemical Engineering, and in this we also highlighted different ways to prepare fibers and where they can be used. For example, they can be used in pH sensing or temperature sensing, and they can also sense some environmental toxicants like metals. Some biosensing also can be done. So there are different applications available in the real time. And electrospinning, here you can see the electrospun fibers can be used as smart textiles, and optoelectronics can be used, and energy harvesters, batteries, food packing, anti-fouling, medical applications, sensory applications. So now I'd like to introduce the perovskite in the detailed form. Here you can see this is the structural aspect of our perovskites. Here I want to introduce the formula ABX3. The chemical formula is ABX3. A site is nothing but methyl ammonium and formamidium or cesium based materials, and B site is occupied by lead or tin or some other bismuth like that kind of heavy metals, and the X is halogens, bromine, chlorine, iodine, this kind of things. And what is the importance of perovskites? Why we want perovskite system? What is specialty of perovskites? In the past, they use some inorganic materials like QD materials like indium gallium or gallium selenide, that kind of metals, heavy metals. But in this case, here you can see the FWHM. FWHM is your PLP. If you study the PL properties, photoluminescence property, it will be very broad. That means your color quality won't be good if you're fabricating some LED, and if you're going to make one LED television, if you want to see that purity, the color quality won't be that good because the FWHM is too broad. The colors won't be that vivid. But if you prepare a perovskite based system with if you want to prepare perovskite based televisions, then in that case, the FWHM is like less than 16 to 25 nanometers. That means your color quality is very good. It is vivid. So you'll be getting very good color quality. So perovskite emitters are quite important for the LED applications. So now I want to stress the importance of instability factors, because I already mentioned that perovskites are good material, but cost-wise and the fabrication wise, because in the past, the fabrication process, you need some clean room facilities and you have to control everything in the vacuum state. But in this case, we can process them in the solution form. So it's quite easier to control. And the instability factors, I mean, the stability in that systems are quite good. It can be used for the long term. But in terms of perovskites, the stability is not that good, and it will be easily degraded because of some factors. What kind of factors is going to govern your stability of your perovskites? So here we can see there are many different factors: light, heat, moisture, oxygen. Those kind of things are going to affect your perovskites. So how you can eliminate this kind of external factors by using some strategies like this. We can encapsulate this kind of perovskite nanoparticles in some polymers or some inorganic materials, or we can form some core shell structures, or we can change the ligands to protect our perovskites, or we can adjust the size of our dopants like that. There are many different ways. This is the formula to calculate some tolerance factor and octahedral factors. What is tolerance factor and octahedral factor? Because I already introduced in the previous slides the structure. Here it is made of A, B, X3 type, right? So if we can control the size of this kind of metal ions, then you can control your tolerance factor. This R is nothing but your radius, ionic radius. If you can control your radius of your atoms, then you can control your structural stability so that it can remain very stable over a period of time. So this is how they can tune our stability. And here, this is another schematic. Here you can see the size, importance of size. Here, the tolerance factor and A cation. If you change the A cation from sodium, potassium, rubidium, cesium, you can see how their tolerance factor is getting enhanced. So if we go up to cesium or Ma or Fa, their tolerance factor is nearly 0.8 to 1 in that. So in that range, it can be very stable. If you're going across this spectrum, then you will be getting the stability is not that good because the size of your ionic radius is getting higher. So your structure will get deformed. So eventually you'll be ending up with a very worse result. So you have to consider this kind of cationic system to build a perovskite molecule. So it's quite important. And here we can see there are different kind of perovskites they use. And if we can tune, because in the past, whatever the materials they use, inorganic based materials, they cannot tune the color. The one material, if you tune a single component, then you can end up with the different colors. That's quite exciting. You'll be getting from violet, blue, green, yellow, orange, red. You can easily tune your system just by tuning your halide components. In this case, you can see MAPB, Cl3. If you change your Cl3 to bromine, Cl to bromine, you substitute them, then you'll be changing your color easily. So if you tune your halide concentration, if you tune your stoichiometry, then you'll be easily getting different colors. So it's quite exciting to work on perovskites. You'll be having very good fun in your laboratory, but the problem is you have to control your stability as well. So it's good. You can prepare the perovskites in a different way, like one-step process, two-step process. This is the precursors they use, and then they heat, they anneal them to form very good quality films, thin films. And then they can also use some nanocrystal pinning techniques in that they use some polymer to pin them. Then they can reduce the defects. And the hot injection methods and the evaporation, roll-to-roll process, recrystallization. So there are many ways to fabricate. And here we can see there are different hole transport and electron transport layer, because we know that LED is composed of two electrode diodes, right? Two electrode. One is anode and the other one is cathode. So if we are going to connect the system to the electrical voltage, the electron is going to pass by your cathode, and we will be having some injection layers like electron injection layer and hole injection layer. If we can tune this, then you can control the flow of electrons and holes. The electron and hole is going to combine, because if your background from material science or physics or chemistry, you will be aware of this system called Jablonski diagram. In that they have showed the importance, how the origin of fluorescence and phosphorescence happens. In this case, usually we know that in our high school we have studied, or in our senior high school we have studied those things. What happens if you are going to pass some energy to your system? It's going to excite. Okay, there are many bands like conduction band, valence band. You just consider that one. Okay, you are going to excite your atom from your valence band. Then you pass the energy. Then it will excite, and it will go to the excited state. Then it won't be stable. Their excited state are higher in energy, so they try to lose their energy and they'll try to come down by this way. So if they are coming down in this way, they are going to dissipate some energy. That energy can be harvested as your light and heat. So if it is happening in two different forms, one is like radiative recombination, the other one is non-radiative recombination. If we control this electron and hole injection process, then we can tune our radiative recombination process. If it radiatively recombines, it will give some light outputs. So you will be getting light out of your device. This is the structure. You can see how the perovskite LED works. Perovskite is going to be the host part that is going to host your electron and hole to recombine and then excite, and then they'll explode with your light. So now we can control the emissive layers performance by using the morphology control or balancing the charges, or we can modify its grain size. These kind of things can be done, and then you can improve the performances. And this is if you have some defects for this. In this case, you can see one is radiative and the other one is non-radiative. If you want to get a non-radiative recombination, that one is good for your solar cells, because in that you don't want the recombination to happen. You want the electron and hole to separate and pass through, so that you will be forming the circuit so you can harvest the energy. But in our case, we are working on photonics. We need the light to come out so that we'll be getting very good energy outputs, energy efficient outputs, right? So in this way it works. And the other one is here we can see the trend, how it works in the organic LED. It takes long time to achieve better external quantum efficiency. It takes long time, whereas in QD LED it's getting faster. But in perovskite LED in recent 3-4 years it's getting very good results. So that we are working more on perovskite based LED systems, and how we can optimize the stability and efficiency, and how to control them, how to counterbalance them. So here we can see there are different kind of perovskites, from 3D, 2D, 1D, and 0D system. If you want to control your 3D structure to 2D structure, we will prefer some ligand-based system. If we can tune the ligands, then we can easily fine-tune our structures in this way. So there are different kind of perovskites, and they use different components like bismuth, aluminum, indium, tin, like that. There are many ways they can form using this kind of chemical components. And how we can tune our stability by using some cation size alteration or active materials and pillars and morphological fine-tuning, or adjusting the work function and balance them, so that you'll be having very smooth transition of your electrons and holes. So here I'm going to introduce perovskites. CS with Br3 is one type of perovskites, inorganic perovskites. Here we are going to blend some polymeric system. So here we can see we are using some polyethylene oxide plus a small molecule and tech small molecule. So we can adjust our carrier balance, as well as we can tune our surface morphology. In the previous case, you can see this is pure perovskites. In this, the perovskites is having very rough morphology. If you want to tune them and make them very finer grains, then you will be getting very good efficiency. In this term, you can see in the pure case, the luminescence, the light output is not that good, less than 400. But if you tune your system by using this kind of small molecules and polymers, then you can enhance your efficiency. And this is another paper we published. And in this case, we are using some interlayer strategy. Why we need this kind of interlayer strategy? Because we know that P.PSS is like a hole injection layer they always use. And the hole injection layer is going to corrupt your emission layer, perovskite layer. So in order to avoid that, we use some interlayer and we tune that layers. So here in the schematic, you can see how we can improvise our crystallinity, how we can improve the grain size quality, like that. So if we use, and we can also manage our stability systems up to 70% relative humidity. So they are stable up to 70% humidity. So it's quite good for the fabrication part. And this is the schematic in which we can see the defect sites located on the perovskites. The red dots are your defect sites. If we are going to defect passivation, if we are going to passivate those kind of defects by using some polymers or some interlayers, that will try to enhance your luminescence by reducing your quenching sites. So in this paper, this is what I have said. In this, the past two projects, we are using perovskite layers with some polymers, and then we use some interlayers. Now we are going to use this kind of system on the stretchable LEDs, the forms of stretchable LEDs. For that, we rely on some PU, polyurethane. Polyurethane is a stretchable polymer commercially available. We utilize that polymers and then we form the electrodes. Here we can see how we start with that. We just start with our spray coating, and then we use our polymer to drop them, and then we cast and take the polymer out, and we'll be getting stretchable electrode. And then we use some hole injection layer and some interlayers like PVP. In the past, we already used that kind of interlayer system. And then we adjust our perovskite emissive layer morphology by using composite polymers like PU, PVP system. And then we use some electrodes to connect it. Then it can work sustainably. Here we can see their performance and their energy output. Here we can see the cross section. From that we are able to say that even after 50% straining the LED, the characteristics, the crystal characteristics of the perovskite still retain the same. So here we can see the FESM, here 0%. The LED luminescence is like this, but if you are going to strain them to 20, 40 like that, the luminescence will quench a little. So here we can see the performances up to 100% strain. It's relatively stable. So it's good for the real-time application. And we also demonstrate the mechanical robustness of our stretchable LEDs. We can attach them onto our fingers, and we can also form some touch responsive devices. In this, we are using some PET spacers. For example, I can show you with the spot highlights here. You can see the PET spaces we use because we have some air gap in between. So the connection between this electrode and that electrode won't get established in the real time. But if you are going to touch them, then it will establish the contact. So the electron and hole will recombine. So you'll be getting the light output. So it's quite interesting. You'll be getting some flexible or stretchable LEDs that can work when you're going to touch. So it's good for the application part. We demonstrate these kind of things. And then we also study the roughness characteristics. And this is the other one, because the last three projects we've done on 3D perovskite materials. Now we try to fine tune our perovskites to 2D structures, because 3D perovskites doesn't have very good efficiency. In order to improve efficiency, we rely on something like 2D structures. For that, we use some zinc bromide addition with PVA conventional ligands, and then we tune the zinc bromide addition slowly, stepwise, from 0.1, 0.2, 0.4. So in this case, we can see how the crystallinity is getting enhanced in terms of 0.2. So that means our 2D perovskites are growing in a very good pace. And here, this is the device performance. And here we can see the current outputs. If we are going to input our current to our system, if you are going to use some lower dimensional structures, your efficiency, your light emission won't be stable. You see the EL emission is getting shifted. Whereas in terms of zinc bromide 0.2, if you can tune your crystal structures, and you will be ending up with your 2D structure, means it is quite stable, and even under high currents, still it retains its color quality. So these kind of systems are quite good and ideal for the real-time application. So we did this part. And the next project, we also do perovskite ligand optimization. In this, we try to form quantum dot structures. Here you can see the TEM image, which is around less than 5 to 10 nanometers, in that range. How we can optimize the condition, because in the conventional system, they use some OA and OAM ligands. But in this case, we are trying to tune that kind of ligands, because ligands are going to protect your nanoparticles or your quantum dots. That kind of growth control is quite important to get some good emission properties. In this case, we compare the conventional system and the DDAB system. Here you can see this ligand is the conventional one, OA, and DDAB is this one, which is sterically hindered, and TOP is more sterically hindered. So which will be giving very good stability and the structural aspects. Here we can see the XRD crystallinity peaks here among AG. if we are going to put some silver, which is going to promote our stability as well. And here we can see the PLQY. PLQY is nothing but a photoluminescence quantum yield. If the PLQY values are quite high, means your efficiency of your LEDs will be good. And we also check the stability towards different solvent, because we are going to process our perovskites in different solvents, right? So if you are going to process and form some thin film, we'll be adding some solvents, and we also use some anti-solvent treatments to form a thin film in order to control the crystal grains. So that kind of system will damage your perovskite sometimes. So in order to test those things, we also check with a different series of solvents, and we check the stability of the PLQY. So still it is good. And device operational stability, we can see which is quite good when we compare to the conventional system. And yeah, here we can see how the FWHM, because I already said that why we want perovskite, because we need a very narrow FWHM peaks. So how we can tune the FWHM when we are going to use this kind of ligands. Yeah, so we are demonstrating those kind of things, and we also study the LED characteristics and the color quality things we have done. And yeah, now moving from the stretchable light emission and photonics, we'll try to get to know about something like sensory application. There are different mechanisms involved. One is like piezoresistive, capacitive, opticals, and piezoelectrics, triboelectric, magnetoelastics. There are different ways, and we have to know that there are different kind of systems need different kind of power consumptions. So depending on our needs, if we are going to put on our wearable devices, we don't want higher energy outputs. Actually, we don't want very high powered electronic systems. So we should build a system which can operate in the low power consumption system, which is good for the applications. So yeah, now I want to introduce something like piezoresistive sensors. In this case, you can see they are forming conductive textiles using some reduced graphene oxides, and then they use some conductive system like hybrid system like graphene oxide plus silver nanowires. So they are going to study the differences among these, how the charge transfer characteristics will be, why we want the composite systems, because we know that the charge transfer won't be good when we are going to use single component system like RGO. When we are going to use some silver nanowires, you can see the differences. They have lysagious charge transfers here, whereas in this case, it's straightforward. You'll be having very good response. It will be very rapid. So these kind of composite structures are quite important. And in the other case, you can also see when we are going to deform your system. For example, if you're going to have your sensory system like this, and if you're going to put the pressure on this, what will happen? You're going to establish the contacts like here. You can see, you can visualize this. This is one thread and this is another thread. If you're going to deform them, the electrical percolations are not good in the initial state, but if you're going to deform to a certain level, it will form the interlocking patterns. So forming porous structures with the very good electrical percolations is quite important for the pressure sensory applications, especially some piezoresistive sensors. And yeah, here we can see how the blood pressure can be monitored. For example, if you want to check your pulse rate, we can put our this kind of sensors onto your body. And here in this picture, you can see they patch the sensor. And then here we can see this is a schematic, because the blood vessels are going to create the pulse when the blood is going to flow. So that kind of small deformations can be transformed into your electrical signal. That electrical signals can be connected to your Bluetooth system and transmitters, and then you can connect with your clouds. Then you can easily monitor from very far regions. You can easily track your patient's record like that. And the other one is textile based. Here we can see the yarns. They are using two different kind of yarns, conductive yarns. When we are going to stretch or bend, it will be having different kind of sensory response that can be tracked with your resistance change. This is nothing but our resistance delta R is nothing but your change in the resistance between initial and the final stage, and divided by initial, then you will be getting this kind of response depending on your pressure intensity. If you're going to press more, the intensity of your connections, the interconnected networks are going to be established more. So depending on that cases, in this case, you can see they are using 0.03 newtons. And if you're going to enhance your load from 0.003 to 3 newtons, you can see the resistance changes. So this is how the piezoresistive sensors work. And this is another one. In this, they are using some leather-based piezoresistive sensors, because we know that leathers have two different sides. One is grain side, the other side is corium side. So if we can print some conductive materials by using some painting techniques they used, and in this they are using this kind of, because which is like a sponge. The other side, the grain side looks like a sponge. This is the schematic, and this one you can see the microscopic view. And if we are going to apply some pressure, here you can visualize they use this system in 0 kPa. When we are going to apply some load 2.5 kPa or 5 kPa, 12.5 kPa, the networks will connect. You can see in the initial stage, the conductive networks are not interconnected, so your resistance will be very high. When we are going to apply some pressure by using the load, then that networks will get connected, so you will be getting the current response like this. Yeah, so you can see when you're going to extend, for example, you're going to monitor your finger motions, then if you're going to extend your motion slowly, then you will be getting very good response like this. So this is how the sensors, the piezoresistive sensors work. And there's another way. They also do some interlocked microstructures. Here we can see this kind of structures they form. They form three different structures in order to optimize which one is the best one: microdome, micropyramid, and micropillars. And they also study the FEA stimulation studies to see the stress concentration in that interfaces. Here we can see the microdome structures and micropyramid. So from this, they are able to optimize the conditions, and they say that, yeah, you can see the microdome structures is getting very good, connections, and then they have a very good response in the current ratio. So this is how they do the sensory applications based on piezoresistive mechanism. And the other mechanism is capacitive sensors, in that they use the same technique, the same structures, but the way they monitor is different. This is how the capacitance, capacitance is derived from this equation. In this, the major thing is this will be constant, dielectric constant for material will be constant, and relative permittivity under the vacuum will be the same, but your area and the distance between the two electrodes will be different. So depending on your pressure, then your area will change and the distance will be changing. So yeah, how you can fabricate this kind of capacitive sensors by using simple techniques, like you can use some textile based methods, or you can use some sponge materials which is having many porous structures, or you can also tune your porosity by using some salt or sugar based composites, and then you can etch them. Then finally you will be getting easily, you can tune your micro roughness, so you will be getting good different results. And now I want to say that when we are going to use this kind of capacitive pressure sensors by using electrospun nanofibers, you can see the differences among 3D and normal structures. Here we can see this is a flat structure. When we are going to use 3D structures with the fibers made interlayers, then you can see the differences, because here the distance between the two electrodes are almost constant. The change is very less. So your sensory response won't be that good, your sensitivity won't be that good. Here you can see the differences among normal one, and if you are going to use this kind of 3D structures, then you will be getting very good capacitance change. That means your sensitivity will be very high. So this is what we need in sensory application. So yeah. And this is the basics about dielectric composites and porous dielectrics. If you are interested, you can go through. And yeah, the other thing is they also use some wireless sensing, because whatever we discussed, that one is wired. You should have some connection to get this kind of response out. Yeah, because we know that it's quite complicated in the real time. If you want to easily monitor, you want some wireless system. How you can create that kind of wireless system? You need some transmitters and receivers. You can easily form by using the conventional systems that they are already available in the market. So you can form that kind of networks, and then you can easily notice the changes in your sensory outputs. And this paper is discussing about, they are using some DNA gel, and they are trying to monitor the biomarkers, and then they are trying to use different kind of networks. Yeah. Okay. And yeah, this one doesn't. And yeah, this one is quite interesting. In this, they are using, they are trying to replicate the same thing what happens in our human body system. They are going to see the mechanical
Participants, mute yourself.
Yeah, here there is another sensory mechanism. They are using a single fiber based sensor, and then here you can see the 0 meter per second velocity. They are going to use to sense this kind of wind speed by using this kind of piezoresistive sensor. They use a single electrode system, and then if you are going to deform by using them by the different wind speeds, then you can see the deformation. Depending on the deformation, we will be getting different resistance outputs. So they are studying the resistance outputs in response to the different wind speeds. And with that, they can easily measure the wind speed. And this is another paper. They are discussing about what is the importance of CNT. We know that CNT is a carbon nanotube, and depending on the sparseness, they can adjust the density of CNT networks. Then they also can get very good mechanically robust systems. And here we can see the differences among the sensitivities. The flow value shows that sparse networks are quite good for the sensitivities, especially for velocity monitoring. And now I want to discuss something called perovskites. Not only they are using for air sensing or body motion sensing, they are also using the perovskites for light sensing, because we know that perovskites have been used for solar cell applications. In this, you can see the detectors how they work. They form perovskite interlayers in this, and they use 2 different electrodes to connect them. And they, in the light, in terms of light, it is going to give the very good current responses, because you know that the carriers will run through the membranes. So you will be getting very good current responses. The other one is transistor type and the memory type, and this one is conventional solar type, solar cell type. And they choose the electrode, and they fine-tune their interfacial structures, and they can also control their responses. Because why we need this kind of photoresponsive system? Because if you are going to use them onto your body, and you are going to expose to the sunlight, if you want to monitor the UV exposure level, then you can easily track how much intense it is. If it is out of the range, you can notice it, and you will be getting the alarm, and you can escape from your threat, right? So this is how we can protect ourselves. So in this case, you can see they are trying to encapsulate the polymer with 4 different kind of polymers they choose, and they blend with perovskites, and they study the transfer characteristics. Here we can see the IDS, nothing but the drain and source. They use this kind of system to study. This is a gold electrode, this source and drain you can consider. You are going to pass the electrodes current, and then you can see the transfer characteristics. They choose 4 different polymers, and they study those things, and they optimize which one is the best one. Depending on their current response, they can study those things. And this is in order to tune the perovskites. I already say they used to fine tune the perovskites by interaction. They use some polymers which is having good functionality that can control the crystal size, and they use some ligands to control the same way here, they are trying to control the size of our perovskite crystals, and then they study the floating gate method they use, and then they study the transfer characteristics. Here you can see in the conventional system like PS they use, it's like 10 to the power 3 ratio, but in terms of P2VP structures, they are getting very good turn on ratios. So these kind of ratios are quite good, so that can be implemented in the real time memory devices. And here we can see this is another flexible substrates they are using, PET, which is very well known because we know that Coke, Pepsi bottles, everything, they prefer using PET. Why? Because we know that PET have very good oxygen barrier levels, so it won't lose the carbonated gases to get through it. So it will be stable, and you'll be having very good flavor on your soft drinks. So that's why they use PET. But PET have very good glass transition temperature in terms of polymers. So they are using this kind of systems to fabricate flexible devices. And then here we can see they are using this system, the perovskite system, MAPBCM3, and then they use the UV intensity. They try to monitor the UV intensity by this kind of system. Here you can see when they increase the UV intensity, the response is getting higher. That means they can track their body sensors like that. Then they can protect their skin. They don't get any allergy towards UV light, right? So the same way here we are using this kind of quantum dot structures in the e-textiles, and then that is going to act as your transport medium. So you can see the differences among without and with. If you're going to use this kind of quantum dot structures, you will be getting better results. The photoresponsivity, you can see how it's getting enhanced. So these kind of systems are quite good for fabricating the real-time devices. And this is another papers. They are discussing about nanofiber system. They are using perovskite nanofibers. Here, they are trying to implement these nanofibers for green and red light photo detectors. Here they are exposing the device towards red emission or green emission. Depending on the light intensity, they are giving the current responses like this. So it's good for the application part. And another one is they can also use this kind of functional composite structures for electromagnetic interference shieldings. So in these cases, you can see how it works. The EMI shielding efficiency in this term, pure one is like 2%. But if we are going to blend this kind of polymeric system and conductive system like this, then we'll be getting very good flexibility. Here in the picture, you can see how flexible it is. And this kind of system is having comparable results like pure silver nanowires or carbon nanofibers. And this is another paper they are discussing about EMI shielding effects. And here they are also using some conventional fabrics, carbon fabrics they use, and then they studied their stability in the ultrasound. They put the materials into the water and they ultrasonic to see how stable they are, and even under flexion how stable they are. That kind of things they have done. And these things are done on something, the commercial one. In this, they want to fabricate some source which can prevent electromagnetic radiation, and which is having very good transparency as well. And they also try to form this kind of interconnected networks. You can see the PSM graphs. And here we can see the thicknesses and the transparency rate. They can control the transparency as well as they can control the shielding. So that is good for the smartphones. You won't have any interactions. And the other one is they are also using some composite structures like graphene silver nanowire graphene structures. And here we can see how stable they are towards bending, and they also have very good shielding efficiency when compared to conventional ones. So they are very good stability, they have very good transparency, and they have shielding efficiency. And this is the schematic. They are showing how the electromagnetic radiations are getting reflected. Only visible lights are getting inside your windows. So that's good for the smart buildings. And this is to portray the importance of FOM. FOM is nothing but figure of merit. If we can control the transparency and the sheet resistance, in this case, you can see the figure D. Figure D is showing 1 by RS. RS is nothing but our sheet resistance, and this one is our transparency. You can plot this graph and find the slope of this one. We'll be ending up with the FOM values. If the FOM is high, that will be having very good performance in terms of wearable devices. So this is how they calculate, and they use this kind of structures for forming EMI shielding applications. And the same how they also do internal multiple reflections, and they also compare nanotubes and nanowires in this case, and they study the simulation effects, and they studied in the initial state bend and twist what will happen to the performances and how these structures are going to give better outputs. So they have studied by using electrospinning. Here, this is the technique they use, and they use some water vapor because they use some PDA polymer, which is water soluble, and then they can form some silver targets over there, and then they use some PDMS layer to extract them out. Then they can finally form film, which is having very good transparency and conductivity. So balancing both these things is quite important, challenging task in this project. And now I want to highlight what is the importance of using this kind of fiber actuators in the robotics, because here they are using some liquid crystal elastomers. Like here, LCE fiber is your liquid crystal elastomers, and they use some graphene, and then they are going to excite them by using some light or some electrical inputs. Depending on the stimuli, they'll try to respond, like our human muscle. If you're going to touch, you can experience, right? You can feel it. The same way this kind of muscle actuators, they can also feel out this kind of actuators. And here in the off state, you can see the initial is like this. And this one under light exposure, if you're going to expose the light towards this material, hybrid material, which can contract 6%, 12%, depending on the intensity, it can contract. So yeah, this graph is portraying the same thing. And this kind of wearable muscle actuators can be used for the robotics, and it can be helpful for the machine learning as well, and for big data collections. And now whatever we discussed, it requires energy. Now I'm speaking about something like self-powered wearable devices. That means you don't want to provide any energy to it. It can harvest energy from your body motions. Okay. So this is another article we published in the recent years. And in this, we have discussed about strain and pressure sensing based on nanofiber system. And we have discussed all the mechanism and what kind of architectures are suitable to do, and what will be the future trends we have discussed. And this one, I want to show what is called perovskite piezoelectrics. I already say that piezoelectrics are going to harvest energy from your body inputs. If you're going to work out, it's going to create the energy, like what we have seen in the past when the kids are walking, the light will glow, right? In that, which is going to transform the body weight to the energy output. The same way here, perovskites is also a kind of piezoelectric material, because which is having this kind of structure. It's going to deform when you're going to apply some stress on it. That kind of stress is going to create the dipolar motions. This is the mechanism. You can see how it's going to work and how the electron flow will happen when we are going to apply the pressure on it and release. It will come back to its original state. So here, this is based on crystalline structures. This perovskite, and this is based on polymer structures. Here we have alpha and beta phases, and here we can see how the dipoles are getting aligned, and depending on your stress, how that is going to work, how they can get aligned and how they can de-align. So depending on that, you will be getting the voltage output. That voltage output can be harvested in the form of energy. So now, I'd like to say the importance of piezoelectric materials, how they can use it for pressure sensing, heartbeat rate. Like here, you can see how they are using this kind of piezoelectric sensors for monitoring the heartbeat rate in the animal samples. They do some modeling, and they use this kind of sensors, piezoelectric sensors. And now, I want to say the present stage research niche, because in the past they have utilized all these kind of structures. Now I want to use this kind of nanofiber based nano microstructures to fabricate. Why we want this kind of structure? Because these structures are water solvent processed and facile processing, rapid manufacture. You can easily, fastly prepare them, and then it's scalable. So this is the method we adapt. This is the schematic. You can see how we start with our electrospinning, and we use some conventional stretchable polymers like PDMS, polydimethylsiloxane, and then we anneal them, and then we etch them, and we'll be ending up with this kind of micro nanostructures with some conductive silver nanoparticles on it. We form them by in situ methods. And this is the way we track our morphological transitions over different steps. And this is the 3D AFM. We can see how the nano crevices are there in our structures. We conform them, and this resembles like our human skin. So yeah, and we can see it's transparent. After doing this kind of etching process, we'll be getting this kind of scalable structures, and yeah, which is flexible, stretchable. And we also study the presence of silver nanoparticles on our system. So yeah, with the FTIR peaks, we are able to show the presence of silvers in the system. And now I want to show the differences among flat and the pattern structures. Here we are studying the surface energy between flat and the pattern structures. The surface energy is getting doubled. In this term, you can see the surface energy is like 12.91. Whereas when we pattern them, it's getting enhanced. That means you'll be having very good adhesion over your substrate. The silver nanoparticle can retain under bodily strain. So it can work in a very good range. So it's good. And we study the sheet resistance and the transmittance with a different deposition time, like 5 minutes, 10 minutes, 20 minutes, 30 minutes. And then we also study the crystallinity characteristics. And then here we can see the mechanical resilience of our material. We compared the flat PDMS and the pattern PDMS, and they are very stable up to 10,000 stretch cycles. We did this up to 40% strain percent. We did. And then we also checked the recovery ratio among conventional flat structures and pattern structures. This means that here from the FEA analysis, you can see the stress accumulation is better in terms of pattern structures. So that implies that this kind of structures are good for forming sensors. Yeah, here we can see the current IV curves and how it is going to experience the current change when we are going to apply the voltage over our substrates. And yeah, from that we can see. And here we can see the 3 different structures and how the stress effects are going to govern the performances and durability studies. Why these structures are quite durable and they maintain its functionality even after that fatigue test. So we studied with the FEA analysis. And here we can see the strain sensors results over 2000 cycles. They are very stable, very small hysteresis, and you can see the recovery ratio performances. And we also study the cell viability, because we know that this kind of wearable devices we are going to put onto our skin, so it will have some cytotoxicity that will affect our human cells. So we have to study those things. So we try to simulate those things with the L929 cells, and then we also study the antibacterial effects, because we know that silver nanoparticles exhibits antibacterial properties. So these devices can sustain with a very good durability and also have very good cytocompatibility. And here we can see how this kind of sensors can be used in finger motion sensing or muscle motion. You can easily monitor, or even for speech recognition, how fast you are, or how loud you are, how the amplitude, what mood you are in. So that kind of things can be easily tracked with this kind of sensors. And we also form strain sensitive pressure sensors. So here we can see how fast it is. It can respond very fast within 30 milliseconds. And here we can see the sensitivity retains even after 30%, like 0, 10%, 20%, the pressure sensor remains same. So their performances are quite good. And yeah, this is the schematic to show why there is a small deviation after 30% in the resistive changes. And the final demonstration, we did this to prove that this kind of electrodes can be used for the optoelectronics. So we did some ACEL devices with the conventional structures like zinc, sulfide, copper structures, and then we also formed some PFO based LED devices, and we studied the luminescence among pattern PDMS and PPPDMS. And yeah, from these results, we are pretty sure that microstructures are quite important for the fabrication of sensory as well as optoelectronic devices. And now I want to stress the importance of energy generators, because last paper we are discussing about sensory application. Now what we can do with this kind of system, why we are doing these systems, we need some energy, right, to drive all this application. Now we need some self-powered devices. How we can achieve those things? We can use either piezoelectricity or triboelectricity. So these are all example for something like nature inspired structures, like they all already do these kind of structures, and muscle inspired structures. And this is to prove that we choose the material based on this triboelectric series. Why we need this triboelectric series? If we have positive and negative terminals, then the charge transfer will be happening like this. Yeah, so if we choose more positive and more negative, we'll be getting better results. So this is the triboelectric series, and how we can choose the material given here. And this is another type of wearable energy harvesters. They can harvest the body heat. Through that, they can convert them to the electrical outputs. So there are different mechanisms involved, and what factors we have to confine. There are many things involved in it. If you are interested, yeah, you can look into the papers. And yeah, they can involve with the different ZT values. If we can use this kind of ZT values in the higher ratios, then we'll be getting very good outputs that can be used for different applications. And yeah, where this is available, where we can utilize this kind of heat harvesting system, thermal harvesting systems. There are different ways we can apply these systems. And yeah, these things we have to consider. If we want to prepare some thermoelectrics, we have to consider their Seebeck coefficient, electrical conductivity, and it should fall within the area concentration. It's quite interesting to do the research on this. If you're interested, you can think on. And yeah, where they can use and what type of fabrication they use. They are showing different ways where they can use power and IoT sensors, deep space machine, because there in the space we cannot provide the energy with the conventional sources. We need to use some renewable sources. So these kind of systems can be helpful. And even for thermal management, it is quite important, and moisture management. And here we can see how the solid, solid and liquid solid structures will work, because the phase changing materials, PCM is nothing but phase changing material. Here, after certain temperature, the phase will change. Depending on that, you can see the visual change. You can see the transparency is getting changed from 25 degrees to 60 degrees. Why? Because the transition happens in that. So depending on that, you can easily track your temperature. And this is another article we recently published. And in this, we are trying to use the triboelectric systems. And we are trying to use some stretchable polymer like SDS. And in this, we are trying to optimize the condition by using two different kind of polymers. One is PTFE and PU. And yeah, finally, we do some PVDF based system, because we know that PVDF is a very good polymer perovskites. We mix the perovskites and CNC, and we form the fibers finally.
Sir, excuse me, sir.
Yes.
Participants, please mute yourself. Gujarat, sir. Gujarat, sir. Gujarat, sir. Please mute yourself, sir. Sir, Lokanath, sir.
Yes, yes.
You can continue, sir.
Yes. Okay, so this kind of we mix with some perovskite pillars, and then cellulose, and then yeah, we form the fiber successfully, and then we choose the PL images, And from this, we can see the perovskite is getting encapsulated in the system so that it can remain stable even after some time. So we combine the perovskites in such a way that we will be getting very good beta phase in the PVDF. And then we compare the normal structures and the PPPNG structure. PPPNG structures are good in terms of voltage generation. So we form this kind of circuits and then we transform them into the rectified voltages and then we study them and we can see the power outputs. And yeah, we can use these kind of structures for e-mask or for shoe soles, cloths, gloves to sense. And then here we can see, depending on your intensity of your motion, you'll be getting different energy outputs. And we study the stability in the first 60 minutes, and even after 60 days, the voltage generation is quite stable. So yeah. And the other one, we also do the recent research on piezoelectrics based on this kind of electrospun reinforced conductive structures. Here we see how we form that. This is the conventional structures. We always start with electrospinning and then we tune them into this kind of structures. So we form two different structures. One is wet spun structure and the other one is ERCF structure. ERCF structure looks like this. They are tortuous. They have many entanglements. So here we can see if we zoom in, we'll be ending up with 50 nanometers nanoparticles on it. And then we form these electrodes to fabricate a glove with some transmitters. And here we can utilize these structures for human machine interfaces. Here we can see how we can respond. If you're going to move your gloves or if you're having some disability, then you can easily convert your thoughts to the others by using this kind of human machine interfaces. And yeah, here we can see how the silver nanoparticles are getting interconnected by using the EDS, and we studied their FTIR peaks and XRD as well and TGA to see the thermal stability. And we form this this kind of ERCF structure we take, and then we prepare this kind of smart textiles by using electrospun PVDF structures over that. And here we can see the differences among mechanical robustness among WCF and ERCF values, and it is quite vivid that we are able to achieve very good stretchability up to 900%, and it is sewable. Even we can sew them in the textiles, and it's quite good. And we can see the differences among conventional structures and the electrospun reinforced structures, and how the stability retained even after ultrasonication and the saline solution immersion, because we know that the textile have a lot of restrictions. They cannot be used like our conventional textiles because it is having some functionality, it is having nanoparticles, so it has to be very stable over a period of time, or it should not degrade even after immersing in solvents. So we have to study those things, and we did those things. It's good. And yeah, here we can see the differences among WSNG and ESNG structures. ESNG is giving very good voltage outputs, and their performances even under 30% cycles, strain cycles, they are good. And you can see how durable they are, and they are very good stability. Even if you're going to blow with the air, they are still stable. Their structure remain whole. They are not getting deformed, or they are not getting separated. So it's good for the application. Now, finally, I want to say that this kind of structures, what we have done, that can be used for your sensory application. That sensors can be connected with human body area networks like this. There are many body area networks like here I have mentioned. So you can look into those things, and they have already prepared this kind of sensors to study many different things like yeah, sugar, temperature, asthma, motion, BP. All these things can be done by this kind of available sensors. And this is the parameters we have to maintain in our normal human body should have. For example, body temperature, heartbeat rate, all these things. So now So how we can track all this? By using this kind of sensors and body area networks and IoTs. So yeah, these are all the things we have to take care, and their energy consumption, data rate, how fast they can transmit all our sensory data. Whatever data we are collecting, it's not like very small. Data is getting collected every second, right? So it will be very big. So the data range, the data rate, it has to transform, because we need some high power internet connectivity, so that like 5G or 6G, so you can easily transform all the data faster. So it's quite good to implement this kind of wearable sensors in the real time. And then you need some good data communication system, and then it should be more secure, and it should be suitable for the real-time application. So there are different protocols they follow, so you can look into those things, and their power consumption is also quite important. Yeah. So these are all the papers I published in the recent few years. If you are interested, you can have a look on it. And these are all the references I have followed in this presentation. If you are interested, please have a look on it. And I'm available on the social platforms. And if you are interested, you can follow me on the pages like LinkedIn or ResearchGate. Yeah, so keep tracking. And now I want to show the natural scenic area in the Taiwan. This is during rainy season. I got few pics, and I want to share those things with you. And this is National Yangmingshan Mountain. This is National Park in Taiwan, very famous. And they have certain regulations, so we should obey them. And we should follow the rules. And this is during some traditional festival. I got some pictures. This is how they celebrate. And this is in central Taiwan, a place called Sito. They have some tea plantation and very old buildings. And they have some wood forest hiking space to work on. So if you are interested to come Taiwan, you can explore those things. And this is my team, and this is my professor, and these are all my lab mates. And I want to thank all my teammates who are supporting me in my difficult times. Yeah, so this is my university's website. You can have a look on it. And if you want to avail some scholarship, you can look into those links. And this is my department. And I want to thank all my collaborators in this time. And I want to thank all my well-wishers, my parents and my professors who built me. And I'm in this place because of all of you people. And I want to thank all my collaborators in this point. And finally, I'd like to thank our organizers, especially convener Shabana Begum and V. Suresh sir, and all the other faculties who are very supportive and inviting me for this talk. I feel you people have some general knowledge about something called what is called wearable electronics, how it works, what kind of mechanism it follows, and what will be the futuristic trend, and what we can do from our side. What computer science background is going to be integral role in this, because not only material science or physicists or chemists are going to give a better output. Everyone have to give their inputs into this, and then we'll create a better environment to live in. So I'd like to thank you all in this time. Thanks for your patient listening. I welcome everyone to ask questions. If you have any questions, you can contact me. If time not permit, we can also have other time to discuss. Thank you. Thank you.
Okay, thank you, sir. Participants, if you have any queries or questions, you may ask, sir.
Hello, sir. Hello. Hello. Hello.
Hello, sir. Lokanatham, sir. Hello, sir. Are you there?
Yes. Hello.
Yes, sir. Okay, sir. Okay,
yes.
sir.
Yes. Audible. Yes. Yeah.
Hello, sir. This is Dr. Nandagopal.
Yes.
This is a very nice presentation, sir. Thank you.
Yes, sir.
And I have only one question that, as per your presentation, says that how to integrate the nano technology into the healthcare technology, as you said, in ECG and other things. can we
Yeah.
integrate into that brain tumors to identify the brain tumors?
Yeah, yeah, it is possible because yeah, it's not
What
like a
type
new
of
thing. They are
sensors
already doing this.
we, yeah,
Yeah,
please.
they are doing it because I'm saying about some basic concepts of how the sensor work or what are all the advantages of using this and that. If you want to have a deep insight about that those things, I can forward some articles to you. You can have a look. In the recent few years, I have seen some neural networks. They are already doing those kind of things to study the brain tumors, or if they want to stimulate that kind of good brain growth or something like what to say, if you want to cure some disease like Alzheimer or something, they are doing those type of things. For that they need some functional materials or like very stable material, because they use some hydrogels or some injectable materials. They can directly impregnate the sensory molecules into your system like nanobots or something. Like your solution, it will be just like mere like a solution, you just impregnate them. In these cases, I'm just showing the solid form of sensors. They are using that kind of liquid form, injectable forms, that kind of sensors. So it's quite difficult to do those things. If we have chance or if we have those kind of facilities, we can think on those part. Yeah, I welcome your suggestion, sir. Yes, thank you for your
Thank you,
question.
sir.
Yes.
Yeah, thank
Yes.
you, sir. Thank you.
Yeah.
Yes, if there are any if there are any more questions, you can ask participants. Okay, sir.
Yes.
That was a wonderful session. Thank you very much, sir. Now I invite Mr. V. Suresh, sir, to propose the vote of thanks.
Good afternoon, everyone. The session was very wonderful. I thank Loganathan sir for taking a session in a very well-mannered manner. You made the things very clear on physiological biosignals and sensors, sir. And also the difference was very clear regarding the variable electronics and variable photonics. And also you made the things very clear regarding metal halide facial fabrication, stable blue perovskite, high luminance and external quantum efficiency, and other sensors, and how they are applicable in our other industries. And it was wonderful presentation, sir. I thank you so much for joining with us and for accepting our invitation to act as resource person for today's session. Thank you so much, sir.
Thank you, sir. Thank you, sir. Yeah.
Thank you, dear participants, for your participation. Feedback link is shared in the chat box and also along with YouTube Live. So you can fill the feedback. So again, tomorrow the session will start exactly sharp at 10 a.m. So I request all the participants to join the session by sharp 10 a.m. Thank you, everyone. Thank you so much, sir.
Thank you, sir. Thank you, sir. Bye-bye. Yeah.
Bye.
Yeah.
Okay, sir. Thank you so much, sir, for your valuable time, and your speech is so good, sir. So we really thank you and for your time and speech, sir.
Okay, okay, ma'am. Thank you, ma'am. Thank you. Okay, thanks for inviting. I hope all the students have got some knowledge about
Yes.
what is called. I don't want them to explore everything. I just want to, yeah, initiate them. I'm just an initiator. I just make them to ignite, and then they can grow by themselves. It's not like whatever we are going to teach, they can get everything. At least they can get 5%, 10%. That's fine. Yeah. Okay, okay, ma'am. Thank you. Thanks for the
Thank
invitation.
you all of the
I hope
participants.
your FDP will. Yes, okay, yeah.
Okay, thank you, sir.
This conference is no longer being recorded.